to talk about the state pattern. There we go. Now it's up there. So for the calculator, so first off, after today's lecture, you'll have all of the content that you need to complete the calculator homework. So today's the last day of content that you absolutely need for the calculator homework. Some of you wanted to start ahead, and I told you to read the references, read about the state pattern, and you'll be able to get a start on it. But after today, there's no excuses. Everything that you need for that homework has been covered in lecture. So today's the day. That said, the next 2 days, if you look at the schedule, Wednesday and Friday are also about the state pattern. So on Wednesday and Friday, we're going to reinforce what we've learned today. We're going to see example after example, probably two big examples. On Wednesday, we'll go over the jumper app that uses the state pattern to control all the physics of moving and jumping around for the player. And then on Friday, we'll have some mystery program because I don't know what I'm doing for that yet. I'll probably come up with some brand new example. And today we'll go over about as simple as we can get and still make use of the state pattern example. So after that, you'll be able to do the homework. The big thing with the homework, if you haven't looked at it yet, it's a 4-function calculator. I'll give you the GUI for it, and you'll get the button presses on your end. And from the button presses, you have to build all the functionality for this calculator, which that in and of itself would be a 115 project, maybe an advanced one late in the semester. But what makes this a 116 project is you cannot use any control flow. You cannot have any of your code executing conditionally. This means no if statements and no loops, because loops could be used to simulate a condition. If you just use the conditional of a loop, you could effectively use that as an if statement. So I gotta say no loops as well. Your code cannot execute conditionally. There are some ways to get around this without explicitly using a loop or a conditional. If you're caught using one of those methods, if it's against the spirit of the assignment, I'm going to look at those and get you on those as well. So no control flow. Your code cannot execute conditionally. So how do we do that? Of course, the answer is going to be state pattern, because I built it up like that. But we're going to see how to accomplish something like this. For the lecture question today, we'll have a simplified example of that. The whole intent of this lecture question is to build up to the calculator, to give you practice with the state pattern, practice with building functionality, conditional functionality even, without conditionals. So this lecture question, no control flow, same rules as the homework, but build some mock-up functionality for a player in a 2D, well, I guess it doesn't have to be 2D, but a platformer. Build some functionality such that the player can run, duck, and stand still, and whether they're ducking, standing still, or running, what's their jump height and what's their movement speed, which should be different based on their current state. So how do we build this functionality without using an if statement? So with an if statement, you would just have some state variables to say, am I ducking, am I standing, am I running? And then depending on those variables, you would say if standing, if running, if ducking, and then return the proper values for jump height and movement speed. How do we do this without a conditional? This one, just like the last double pointer, this is a 20-pointer, and you'll have till Tuesday night, tomorrow night. Just like the last one that was a 20-pointer, you really need this background to be able to tackle that calculator homework. So I don't want anyone skipping this. I'm going to incentivize it with a later deadline and more points. I can't have you skipping this because you're just going to sink yourself on the calculator homework if you don't have this practice. I saw that last semester. A lot of people skipped the lecture question leading into calculator. It caused a lot of problems because nobody had hands-on experience with the state pattern, and they tried to dive directly into the calculator, which is just a setup for failure if you try that. So we're going to incentivize this, and hopefully y'all do this one and then do well on the calculator homework as well. Okay. So enough lead-in. Design, well, I guess one more slide of lead-in. Design patterns in general are approaches to common programming problems. There are a lot of just common problems we face when we're developing, a lot of things that reoccur over and over and over again. So design patterns are uniform-ish solutions to be able to tackle those problems. When you have a problem that keeps coming up, let's just have one solution, apply that solution, apply that structure, apply that design to that solution, and then use that design each time you come up with that problem. There are a lot of these. This is kind of a rabbit hole you can go down studying design patterns. It can be a lot of fun. It can also be a bit dangerous if you get a little overboard with it. If you're interested in a lot more of this, try searching the Gang of Four. They're the ones who popularized the term, or I guess invented the term, design patterns, and they came out with a whole list of design patterns that they thought people should use specifically with object-oriented programming. We're only going to focus on the state pattern in this course to give you a taste of what design patterns can do, and then you're certainly going to see more as you progress through your programming career, but you're also encouraged to study on your own to see what other design patterns are out there and what other things you can find useful in your programs that you're building. And the main goal, of course, right in the name, improve your design, but also improve the maintainability of your programs. We want programs that are easy to design and easy to maintain. So for 115, the programs were always small enough that you could just wrap your head around the whole program and bang out the code. In 116 and beyond, when the problems get a lot larger, the programs get a lot larger, you got a lot more code, we have a lot more need for proper design. So we don't spend a lot of time building messes of programs that are almost impossible to maintain, and maybe more importantly, nearly impossible to debug. If you have a bug in a program that's just one giant main method with a whole bunch of conditionals and stuff in it, it's going to be almost impossible to find that bug. Sure, you'll be able to do it, but it could be a lot easier if you have good design, a well-designed program that allows you to identify the bug a lot easier. So the state pattern, we're going to use polymorphism. There is a reason we cover polymorphism. It's, well, because it's useful in general, but also it's going to enable us to actually implement the state pattern the way we're going to see it in this class. So we have objects. We have classes where we can create objects, and we have objects that contain state and behavior. We have state, which are the variables in that object, and we have the behavior, which are the methods of that object. If we want to change the state of an object, we just change the values of those variables to change the internal state of that object, and that state can affect the behavior. Maybe we have some methods that do depend on those state variables to generate slightly different behavior based on the state. But what if we want significantly different behavior in an object? If we want an object that, depending on its state, has wildly different behavior, but is still the same object. So we could do this with just a bunch of if statements. We can certainly do this. We can have some flags as state variables that maintain the state, and then say if this flag, we have all of this behavior, else this flag, and we have all of this behavior, and put two different pieces of behavior in the same method. And this is our first level approach. This is a level 1 approach. What we do, we had a sum method, and if some conditional based on my state, behavior, else behavior. So we effectively have one method that can do two very different things depending on the state variables. Now again, if the state variable is like the cost of an item and you're just returning some function of that cost, that's a bit different. What I'm talking about here is significantly different behavior where depending on this state, I want to do completely different things. So for the lecture question, if a character running in a game, that character is going to have significantly different behavior than if they're ducking in that game. Which maybe not completely captured in the lecture question, but I wanted to keep that simple since we're just returning ints. But we could have very different behavior based on those two states. So we can do this will work. But what about maintainability? What if we have a lot of different behaviors that we want to implement? And depending on the state, we might have a lot of different conditionals that are true, and each one of those conditionals is going to vastly change the behavior of this object. This method is going to be completely different based on some criteria, and maybe we have 5 different, completely different behaviors depending on those conditions. Well, yeah, we can still do this with a giant if block, but once all of our methods are looking like these giant if blocks and we're jamming all of this vastly different functionality into one class, Well, our code's going to get harder and harder to read, harder and harder to debug, harder and harder to test, and harder to maintain if we want to add more functionality. What if we want to add a sixth behavior? We got to figure out where in this if block to put it. And we have to make sure that that conditional doesn't override any of our other conditionals and break any of our other behavior. And depending on each one of these behaviors, each behavior might be changing our state variables. So we got to keep track of all that and figure out how to do this without really just being a complete pain to code. How are we going to do that? So this is where the state pattern comes in. The state pattern says, okay, that could get very painful if we have these giant if blocks all over our code and all these else if statements. So let's try to organize this a bit. Let's try to have one common approach where whenever we have such a problem, we're going to go in and apply a common solution, a common strategy that we go in to solve this kind of problem. So this is where we'll use the state pattern. And instead of putting all of that behavior in the same class, what we're going to do is take that behavior out of that class and create a separate class for each behavior that we want. So each behavior that we want is going to be in a separate class and implemented separately from the main class. And then in that main class, we're going to have a variable that stores the current state. So we're going to have a class for each state that the object can be in that controls the behavior in that state, and then store a variable with that state, and then defer to that state whenever we have to figure out what functionality to use. So if we set it up like this, we're going to make decisions based on the type of that state. Depending on the type of that state, we're going to behave differently, as opposed to checking some value and saying, as a conditionally on this value, I'm going to change the behavior. So we're switching up how we're deciding what behavior should be used. This is going to help us, we'll see when we get to the examples, but we're going to have a lot more classes and a lot more files in our code, but each file and each method is going to be significantly smaller, which means it's going to be significantly easier to test each piece of functionality, and easier to expand and easier to read. So for this, we'll need a state class that's going to be an abstract class. It doesn't have to be abstract. It could be, in Scala, what's called a trait, or in Java, what's called an interface, which is effectively an abstract class with no implementation at all. It means none of the methods have definitions. It's just a bunch of method headers that need to be fulfilled. Abstract class is if we add any functionality at all to that class, it's going to be an abstract class. So a little vocab. There are differences. I'm not going to get into them quite yet. Probably not in this class. Maybe in passing. But the difference doesn't come up unless we're doing multiple inheritance. We're not going down that road quite yet. So we're going to, in that abstract class or trait, we're going to define an interface, which is all the methods that can be called on the state, which is going to be all of the methods that we want to defer to the state for functionality. And this is going to be called our API, or Application Programming Interface. You may have heard this before. An API is how you access a certain part of functionality programmatically. So how do we access this functionality? It's through the API. In this case, the API is just a list of methods that can be called. And then each state is going to implement what we call concrete classes or concrete state. I'll call them in this example. Each actual state that we could be in, we're going to extend that state class and implement all the methods in that API so we can have the functionality defined for each particular state. And then each state as well will have a reference to the object to which it's attached. So if I have an object with this state has to know what it's attached to, so it can, one, access the state of that object if there is any, and two, can change the state, can replace itself with a new state. Okay, so that's a lot. That's like all the definition of a state pattern. Technically, you can know what the state pattern is right now, but holy crap, what did all that mean? So let's see an example to see what that actually looks like in practice? How do we have an object that defers its behavior to state objects through this state API, through a state abstract class with concrete implementations for each state? And for that, we're going to look to our good friend Bruce Banner as an example. So Bruce Banner, if you don't know, he's a world-class scientist. He's extremely smart. He's able to drive a car, which will be relevant in a little bit, but he's not very helpful in a fight. We call him, when he's acting like this, we call him Dr. Banner. However, Dr. Banner has another side. If you make him angry, he becomes the Incredible Hulk. The Incredible Hulk is wildly different than Dr. Banner. He smashes cars instead of driving them. He's great in a fight, but he's completely out of control. So this is the same person. They're both Bruce Banner, but Bruce Banner can be in two wildly different states with two wildly different behaviors. They're going to behave completely differently beyond what we would want to do with just a regular state variable. We would have to have a state variable that says, is he currently the Hulk? If he's currently the Hulk, behave completely differently. And we basically have two completely different behaviors built into the same class. We don't want that. We want to use this state pattern to be able to separate the two different states that Bruce Banner can be in. So they're completely different, and we want to use that state pattern to capture this different. I'll sprinkle in the program, I'll mix the programming and the example codes, but we want to get this different implementation, this different functionality from the same class. So to do this in programming, we'll create a Bruce Banner class who's going to have a state variable storing which state he is currently in, and then defer all our functionality to that state. So we'll create a Bruce Banner class. We're going to have four methods here. We want to know Bruce Banner in his current state. How does he do with cars? And how does he do in a fight? These are the two different pieces of functionality we'll look at just for this example. Of course, there's a lot more differences between Dr. Banner and the Hulk, but these are the two that we'll look at for this example. And then two other methods. There's two things that we can do which are going to affect his state. We can either make him angry or calm him down. If we make Bruce angry, he's going to become the Hulk. If we calm him down, he's going to be turned back into Dr. Banner. For this functionality, we're going to have one state variable or one instance variable or field, whatever you want to call these. I like calling them state variables just because I'm leading into the state pattern. I'm going to have one variable storing the state, and I'm going to create a state object from the Dr. Banner class and pass that class a reference to Bruce Banner using the keyword this. So a lot going on in this one line. But I'm creating a new instance of Dr. Banner, which we'll see the implementation of that on the next slide. But importantly, this is an instance of Dr. Banner, so he's going to start initially in the Dr. Banner state. But I'm storing that state of Dr. Banner in a variable of type state. Dr. Banner, the class, extends state, so I can store it in a variable of that base class, that base type state, instead of a variable of type Dr. Banner. So this is where we're going to apply some polymorphism to implement this state pattern. And then all these methods, Bruce Banner doesn't implement any functionality at all. In this case, we're just going to defer to the state for every single one of these methods. We're not going to implement anything here. We're just going to say, hey, state, what do I do when somebody makes me angry? What do I do when somebody calms me down? Can I use a car? How am I in a fight? So we're going to create a state abstract class, which is going to take a reference to a Bruce Banner. Bruce Banner could technically be an object here instead of a class. There's only going to be one for practical purposes. So we're going to give the state an instance of Bruce, and any state that implements, that extends the state, has to implement these four methods that Bruce is going to defer to the state for implementation. So make angry, calm down, use car, and fight. The state is only defining the API. It's only defining the methods that are going to be called, but there's no implementation in the state itself. Now, when we actually want to create our two states here, the Hulk and Dr. Banner, we're going to have our constructor take a reference to Bruce Banner so we can pass it to the state. And then we're going to implement those four methods with whatever behavior he's supposed to have in his particular state, whatever state he's in. Is that a question up there? No? Okay. So for example, when he's in the state Dr. Banner, we're going to say new Dr. Banner, give it a reference of this, whatever object we're currently in of type Bruce Banner, and then defer to that for the functionality. And then that functionality is going to be, if he's calmed down, okay, he's already calm. Use a car.drive. I didn't show the car class here, but the Boolean there is overweight. So false, he's not overweight for this car. And then fight, well, he's not going to do so good in a fight. Of course, if we were building out the full example, if we were using this in a program, we'd build more functionality there. Here I'm just using print statements to say we would do something that we've learned for the past semester and a quarter. We would build all that stuff here. I just want to focus on the state pattern for now, so I'm just using some print lines that don't really do anything. The one that I want to focus on is this one right here. When he's in the Dr. Banner state and somebody makes him angry, that's when he's going to become the Hulk. To do this, we're going to access that reference to the Banner class. We're going to access that reference, which means we have access to that state, and we can replace that state with a new state. And in this case, we're going to replace it with a new instance of the Hulk. So we're going to change his state. So the behavior when he's Dr. Banner does involve, when you make him angry, his state changes to the Hulk. And we call this a state transition. So we can have these state transitions in other states. And this state is actually replacing itself with a new state. So the behavior is changing based on what's happening here. Then when he's the Hulk, similar, but when you calm him down, replace that state with a new state of Dr. Banner. So he's going back to the Dr. Banner state when we calm him down. Now, when we create a new Bruce Banner class, he's going to start off with all the functionality of Dr. Banner, everything implemented in the Dr. Banner class, until we call make angry. That make angry is going to defer to the Dr. Banner.make angry, replace his state, and then he's going to have different behavior after that. So in this way, we can use the David Banner class, and when we're using that class, we don't really have to think about all his state changing and all his behavior changing. We just call these four methods, and maybe sometimes the state changes, maybe it doesn't, but all of the appropriate behavior is going to be reflected just by using these four methods, deferring to the state, and having the state update when certain methods are called when we hit one of those state transitions. So in the Bruce Banner class, you notice the Bruce Banner class doesn't even have any mention or reference to the Hulk state, but he can go into that state based on starting in the Dr. Banner state. We're just deferring to the state, we're defining the initial state, and then deferring to the state for all our functionality. This class doesn't even know when the state changes, nor does it care. And that's the beauty of this. I won't say never, we're actually going to change it in these various slides, but we don't really have to change this class when we add more states and more functionality. We're not revisiting this class. This class, for the most part, is done. We're just going to change the states and change the state transition if we want this class to have different behavior. So it's very easy to expand a class when we use the state pattern to add more complex behavior to a class. It's very easy to expand. Where if we have a whole bunch of if statements and crazy twisted logic, that can very quickly become a mess to be able to add new functionality. But now, adding new functionality, not that big of a deal. Oh, I got ahead of my slides there. So these state transitions, we have different behavior. We have a state transition by accessing that reference to the object to which the state is attached and replacing its state directly. I'll note here, if you look at the Wikipedia article I linked at, or a lot of different resources, there is a different way to do this. Instead of taking a reference to the attached object as a constructor parameter, there are approaches where every single method will take that reference as a parameter. Personally, I just think that's a little, it's a little repetitive. Every method has to have that reference. But there is a good reason to do that. It's so you can have, instead of an abstract class for the state, you can have a trait for the state, which means you can have multiple inheritance. It's not a road we really have to go down right now, but that is another option. And that is the more common option that you'll see out there. So if you notice that, either approach is fine as long as you don't have some multiple inheritances and some weird stuff going on with your OOP. And if you want to implement your code using the other approach, you're more than welcome to do that. It's not going to hurt the graders at all. Okay, so we got it with two states, but really, arguably, maybe not even an argument, it's just probably easier if we just did that with an if statement. Just have a Boolean flag as a state variable is the Hulk, and do it that way. It's only two different behaviors. Each one of those four methods just needs one if statement, one if, and one else, and have double behavior in each of those four methods. Not really that big of a deal, and it probably is cleaner code because you don't have four classes, you just have one class. So you have all your functionality more condensed into one class, and the whole class would probably be 50 lines of code. It's going to be pretty easy to just brute force read through that. So the argument's pretty simple to say, why would we use state pattern there? But really what we're after is the maintainability, which specifically means when we want to add more functionality, it's no big deal to add more functionality. So let's meet Professor Hall. Minor spoilers if you haven't seen these movies. So let's meet Professor Hall. This is Bruce Banner transformed to the Hulk, but with full control over his anger. Where the Hulk is just completely out of control and just smashes everything. Professor Hulk has the intellect of David Banner, of Dr. Banner, but the strength of the Hulk. It's the best of both worlds, and he's just got it together. And he's great in a fight and can drive a car. For our purposes here, for this example, he can do both. He can do something that takes some intellect and hold his own in a fight. So let's implement this class, or this state. To do that, we'll create a Professor Hulk class. Same header, we're going to extend state, have the same constructor that takes a reference to David Banner, or Bruce Banner. Just implement the four methods. Same thing that we did with the other two classes. When I go through this, I'm not thinking all that much when I'm designing this. I'm saying, if he's in the Professor Hulk state, what behavior does he have for each of these four methods? I'm not worrying about a big if block. I'm not worried about interacting with any other states or any other code. I'm just saying, when I sit down and write this, okay, when Professor Hulk is made angry, what happens? Well, it's no big deal. When Professor Hulk is calmed down, well, he's already got it together. It's no big deal. When Professor Hulk uses a car, he's going to be able to drive that car, but he's going to be overweight. He might damage the suspension or whatever, but he can drive that car. When Professor Hulk gets in a fight, well, he's going to be pretty deadly because he doesn't only have the strength of the Hulk, but he can actually control it and have some more strategy instead of just smashing wildly. And then we have to add some state transition. We have to get into the state somehow. And we're going to put that right in the Bruce Banner class. There are other ways we could do this. But we'll put it right in the Bruce Banner class, add this learn control method, and once he learns to control this, control his anger, he's going to move into this Professor Hulk state. So we added a new state, we added a way to get into that state, and we didn't even touch any existing functionality. We did not edit any single method that we've already written. Of course, we could have if we wanted to add a different state transition. If we wanted to add more transitions, we'd have to make some minor changes to other files. But we didn't have to modify anything to be able to get this new state and this new functionality. Which means we don't have to retest anything. All that, the other two states that we've already tested, we already know they work and everything. We don't have to retest that. Our unit tests that we write for those It's all good. It's all still reusable, still fine. And note that since we added this learn control right in the Bruce Banner class, that Bruce is going to have this behavior no matter what state he's in. So whether he's Dr. Banner or the Hulk, in either one of these states, we'll let him learn control. No matter what state he's in, he can learn to control this and become Professor Hulk. So he has this behavior. If any behavior is common across all states, we can put it right in the actual class with the state itself to share that behavior across all states. We could also add this to our API, add it to the state class, and have him behave differently in his different states. But we'll say he can always go to Professor Hulk. And also note that there's no going back. We didn't add any state transitions from Professor Hulk to his other two states. Once he's Professor Hulk, he's there for good. At least in our simulation here. So we have these three states and the state transitions. What's really helpful when we have this, when we're working with the state pattern, is to draw what's called a state diagram. So we have these three states, and when we implement each state, we're going to implement all of the methods in the state class based on how he's supposed to behave in each one of these states, and the state transitions between them. So we want one picture that's going to kind of capture all the different states and all the different state transitions, and we're going to do that using a state diagram. So we start, so we're going to start in the initial state of Dr. Banner. If you make Dr. Banner angry, he's going to become the Hulk. So that make angry implementation in Dr. Banner has to have a state transition that moves to the Hulk. Sometimes these methods will have other functionality as well, but somewhere in that make angry method in Dr. Banner, we have to have a state transition over to the Hulk. The Hulk, calm him down, he goes back to Dr. Banner, and from either of them, if he learns control, he's going to become Professor Hulk, and once he's in the Professor Hulk state, that's an end state, he's staying there forever. There's no going back after that. So this is one picture that gives us the design of our program, of our states. This can also be referred to as a state machine. You'll see finite state machines. Actually, I think we moved that to 191 now. You might have already seen this. If you've seen finite state machines, very similar thing here. So especially when we have a lot of states and a lot of complexity, like you will for the calculator homework, it's very helpful to draw these out. Draw all the states you have and all the transitions between those states to capture every piece of different behavior that you can have. And just I've seen a lot of students go down the wrong paths in the calculator homework last semester. So I'll throw it out there. My calculator solution has 6 states. So if you have significantly more than that, you might want to refactor and rethink how you're going. You could easily have 9 or 10 using similar approaches. If you have a different state for each of the 4 functions, I jammed all those into one state. You can get it down to 6. Possibly lower than that. I haven't really tried to crunch it down more than that. But 6 pretty reasonably. So when you're applying the state pattern, like you'll do for the lecture question, like you do for a calculator, I would do this, and I do this in 3 separate steps. 1, define your API. Go into your state class and say what methods are going to change based on the state that I'm currently in. If any behavior changes at all based on whatever state I'm in, it's got to go in my state API so I can implement it differently in each one of my states. Oh, and worth mentioning, I didn't mention it before, but of course in all of this code with 3 different states, then use a single if statement or loop and all of that. So should go without saying, but just a proof of concept for the homework and lecture question. So write the API. Any behavior that changes depending on state, put those methods in your state class, then put those methods in your root class, your class that's going to contain the state, and write those same methods but defer to the state for the implementation. So the behavior of those methods changes based on the state. You're just going to defer to the state and work through, using polymorphism, just work through the state class, that base class, and not worry about what concrete class is currently being used for that functionality. Then decide what all your states are, and the order can be different. Maybe you want to figure out your states before your API. The order can be different here. But decide what all of your states are. What different states can I be in? What possible situation can I be in where the behavior is going to be different? So right after if I hit 3 plus 2 equals, what's the behavior of every single button on that calculator? Is it different than any state that I already have defined? Well, it's going to be a new state if it is. If I hit 1, 3, decimal, am I in a different state? Should I have different behavior than when I first turned on the calculator after hitting those 3 buttons? Yeah, probably. I got to disable that decimal button somehow. So I'm going to be in a different state. That's another state. Every time you have different behavior, when you can be in a different state, it's another state. That's another class that extends your state abstract class or trait if you want to do it as a trait with no constructor. And then finally, determine all the transitions between the states. So I have all these states. I have the interface defined. I have the methods implemented in each one of my states. Now how do I transition between these states? Draw out that whole state diagram. And once you have the whole design, it's time to go to the code, start implementing those things. So this calculator homework is much, much more of a design homework. You should spend quite a bit of time drawing out state diagrams and thinking about how a calculator behaves. How do you implement all the functionality of a calculator? Because in the document, I just give you a big bulleted list of a bunch of functionality. It's not written as a state diagram. So your first task is to take that big list of functionality and try to figure out how that fits into a state diagram. And I find it helps to, the functionality is very similar to any calculator you're going to find on your OS. Just pop open your calculator and start hitting buttons. How does that thing behave? If you don't want to just read through bullet point after bullet point. How does that thing behave? How is it different for each state that you can be in? What are those states? All right, any questions at this point? That's quite a bit. That's a state pattern in a lecture. We'll reinforce it for 2 days. But any questions at this point? Okay. So we're back to the lecture question. We have the API here is defined for you. You got to figure out what states you can be in. Well, the states are pretty much given to you: standing, running, and ducking. So what's the behavior for each one of these? What are the state transitions that we need? And how do we implement all that? And I do have, if you go to the bonus slide, the state diagram. If I'm ducking and I go to stand still, I'm going to go to standing. If I'm running and I go to stand still, I'm going to standing. If I'm standing and I duck, I go to ducking. If I'm standing and I run, I go to running. If I'm ducking, there's no way to go directly from ducking to running. There's no way to go directly from running to ducking. I have to go through the standing state. And then I jump and speed. Those two methods that return those values, they need to behave differently for each one of these methods. Just in case somebody misses this note, this is an important one. I got to read this. If you have one big project with all of your lecture questions in it, I know a lot of you do, and that's fine. I encourage that even. But if you zip that entire project and submit it, it's not going to work at all because you're going to have control flow in those other files. My grader is looking through all of your submitted files for control flow. So that's going to break. It's going to not compile. It's going to give you a 0. So make sure when you submit, you're only submitting the code for this particular lecture question. Either start a new project or put it in your existing project, but only zip up the platformer. Only zip up the platformer package. If you go into your OS, go to that directory and just zip that directory. That'll also work if you want to still keep everything in the same project. But just a heads up on that. If there's any if statements anywhere in your submission, it's going to break. Anywhere in your .scala files anyway. All right, with that, with the last 7 minutes, I'll walk around. Other than that, see you Wednesday.